Well, welcome back, folks. We are going to finish up our last video on the stoichiometry unit today and talk a little bit about percent yield. Stoichiometry is, I lost my train of thought. What I'm trying to get at is that when we are in a lab and we're performing an experiment, so let's say we're doing an experiment and we start with so many amounts of the reactants and we try to get this amount of product. Well, as you know, experiments don't always go the way that we plan. So we use percent yield as a way to determine how accurate our experiment was. So we compare what we actually get to what we calculate we should get, and that tells us our percent yield. So we should be able to calculate this fairly easily and incorporate this in some of the stoichiometry concepts that we have discussed as a class already. So you should be able to understand the concepts of theoretical and actual yield as well as calculate percent yield. By the way, the word of the video today is Purdue, as in Purdue University, which is where I graduated from college. So make sure you write that down in your video notes as we move forward. Some actual key vocabulary terms here include the actual yield, the theoretical yield, as well as the percent yield. So when we actually do stoichiometry, we're calculating the theoretical yield, that is what we should get from the reaction. So we start with this amount of chemicals, and we mix them together. We should get this amount of product at the end. Now, when we perform an experiment, the amount that is produced is known as the actual yield, which is what we actually get when we perform the experiment. So theoretical is based on calculations, actual yield is based on experimental data. Now, these numbers can vastly differ depending on how well we actually perform an experiment. What we're going to do at the end of the year is actually start with copper, and we're going to go through a series of chemical reactions, and based on your chemical technique, you should get all of the copper back. So we'll do a percent yield calculation to calculate this. But keep in mind the differences between actual and theoretical yield, as well as understanding that the actual yield can greatly differ from the theoretical based on how well you perform the experiment. So the relationship between the actual yield and the theoretical yield is known as the percent yield, and we can plug in the numbers and solve. It's pretty straightforward. We just take our actual yield, which is what we get in our experiment, we divide by the theoretical, and we multiply by 100. Hypothetically speaking, if we were to get 50 grams as our theoretical yield and we performed the experiment perfectly, we should get 50 grams for our actual yield. We divide those and multiply by 100, and that gives us our percent yield. If we have less than that, that means that we didn't get as much as we should from our experiment, and if we end up with a percent over 100, it means that something went horribly wrong because you somehow managed to create matter. So congratulations to you, you have just broken chemistry. So how do we go through and calculate these types of problems? Well, let's look at a couple of practice problem examples here. So practice problem number 1 reads, if 4.50 grams of HCl are reacted with 15.00 grams of CaCO3, according to the following balanced chemical equation, calculate the theoretical yield of CO2. If 2.50 grams are isolated after carrying out the above reaction, calculate the percent yield of CO2. So we got a couple things that are going on here. First off, nice, we are given a balanced chemical equation. That's going to make things a lot easier for us. Also notice that we are given grams of one reactant and grams of another. And it's asking us to calculate the theoretical yield of CO2. So this not only is going to end up being a percent yield, but notice that we have two different reactants. It is a limiting reactant problem. So we're going to need to convert 4.5 grams of HCl to grams of CO2 and 15 grams of CaCO3 to CO2 in order to determine the actual theoretical yield. So let's go ahead and start with grams of HCl. So we start with 4.50 grams of HCl. And again, now this is a basic stoichiometry problem. We need to convert grams into moles. And again, I find that information on the periodic table. We're going to go moles of HCl. Again, whatever's on top of the first step goes on the bottom of the next. We want CO2, so we're going to convert to moles of CO2. Remember, the only way you can change the chemical is from one mole to another. We look at the coefficients of the balanced chemical equation to determine our subscripts, 2 and 1. And our last step here, moles of CO2, and we're going to get that into grams of CO2. Again, you find that information on the periodic table. Now we're going to do some math. So plug this into your calculator and get your theoretical yield of CO2 from that amount of HCl. So our theoretical yield for this is 2.72 grams of CO2. Okay? Now what we need to do is we need to do the calculation using CaCO3. So let's start. And we need to convert grams to moles. Again, find that molar mass by using the periodic table. Whatever unit's on top of the previous step goes in the bottom of the next. You're probably sick of me saying this all the time. And what do we want to get to? We want to go to CO2. Again, use the coefficients of the balanced chemical equation. So it's going to be 1 and 1. And again, anytime we go moles to grams, we find that information on the periodic table. All right. Let's do our calculation here. So what we get here is 6.543 grams of CO2. Well, again, with the limiting reactant problem, we need to figure out which one is less. So that one is less, so therefore that is the correct answer. All right, so that's the first step of the problem. No, that's quite a lot of work for just one step. Let's look at the second half of the problem and then go from there. If 2.50 grams are isolated after carrying the reaction, calculate the percent yield. So we're given our actual, we have our theoretical, we can now calculate our percent yield. So what we're going to do is we're going to take 2.50 grams of CO2. We're going to divide that by 2.72 grams of CO2. Whatever we get there, we multiply by 100, and that gives us our percent yield. And what we get, using correct significant figures, is 91.9%. Okay? So again, when you do your math, you get your theoretical yield, which is what this is up at the top, theoretical. Your actual yield, notice it says something like is isolated, is created, is actually produced, something along those lines to let you know that it is your actual yield. So keep those things in mind as we go through and complete these types of problems. Let's do one more practice problem, just to be sure. Phosphorus reacts with bromine to produce phosphorus tribromide. If 35.0 grams of bromine are reacted and 27.9 grams of phosphorus tribromide are formed, what is the percent yield? So the first thing we need to do here, notice we are not given an equation, so we're going to have to write that out. Phosphorus reacts with bromine to produce phosphorus tribromide. So let's go ahead and write that equation first. So phosphorus, P, reacts with bromine. Remember, bromine by itself is part of the diatom, so it's Br2. Produces phosphorus tribromide, so PBr3. We need to go through and balance this equation. So notice that BRs are 2 and 3 on each side, so those need to become a 6. So we're going to put a 2 there, 3 there, and that gives us a 2 in front of phosphorus. All right. Now that we've written our equation correctly, let's take a look at what else we need to do. If 35.0 grams of bromine are reacted and 27.9 grams of phosphorus tribromide are formed, what is the percent yield? So what we want is percent yield. I'm given a starting amount and how much is actually produced. So remember, this is your actual here. All right, so what we're going to do is we are going to use this information here, convert that to PBr3, and that's going to be our theoretical, and then we can do our calculation. So let's start with some stoichiometry again. 35.0 grams of bromine. Remember, whatever unit's on top of the first step goes in the bottom of the next. And again, we're going to convert that to moles so that we can switch the chemical. Remember, it's Br2, so we need 2 bromines in our molar mass calculation. We're going from moles of Br2 to moles of PBr3. Again, use the coefficients of the balanced chemical equation. One more step. We go from moles Now we do our calculation to get our theoretical yield. So our theoretical yield here should be 39.5 grams. Okay? We need to do our percent yield calculation. So again, we need to take our actual, which is what's given to us in the problem, divide by our theoretical. We multiply that number by 100, and we should get our percent yield. Which rounds out to about 70.6%. Okay, so again, these may have some stoichiometry problems attached to them. Remember, what you calculate is your theoretical, what is produced or actually made is your actual. So I know there's a lot of math here, but keep in mind this actually isn't really a big stretch of the imagination. We've built up your stoichiometry stamina, so to speak, as we have worked through the previous videos. So keep in mind that the actual yield is what is produced in the actual experiment, and your theoretical is what you use. Your theoretical is what you calculate using stoichiometry. Keep in mind that the percent yield is the actual yield divided by the theoretical multiplied by 100. So the calculations are not that difficult. We just need to incorporate our stoichiometry as we go through and complete this. Hopefully you have a really good idea of what's going on in this video, folks. We will talk to you next time. I hope everybody has a great day, and we will talk to you later. Bye-bye.